But Conscia was founded in 2003 in Denmark. And as you can see from the map, we've moved to many different countries. Last year, we moved into Great Britain. Personally, I'm sitting in Norway. And one of the really cool things about working in Conscia is that even though we're in different countries, it doesn't feel like we're in different countries. At a regular week, I will talk to at least 3 or 4 of our different countries and my colleagues there, which is fantastic for sharing our skills, our knowledge. We have a network of knowledge. We have virtual teams. In fact, Conscia aims to be the best place to work in Europe for talented IT infrastructure specialists who have deep technical knowledge. You'll find many of those in Conscia. We've grown quite a bit since 2003. We're close to 1,200 people, and over half of those are engineers and analysts. So we're definitely technical nerds in this company. And we're so lucky to have many of our customers who trust us to build their critical infrastructure and make sure that they're as secure as they can be for the threats that are out there. And as you can see, we have above average happy customers and above average happy employees. And of course, we also make a bit of money. Our technology strategy is now on 3 pillars. Most of you know Conscia. If you know Conscia from before, you know us as the excellent infrastructure company, the networking side of our company. If you're in Slovenia, you definitely know our cybersecurity brand. And we are focusing on these 3 things. So cybersecurity, networking, and hybrid cloud, and also how these all interact and integrate together. Because we know that they're not separate silos, they all interact. One of the cool things about Hypershield, at least as far as I've understood it, is that it touches on all of these areas. It's a cybersecurity product, or I like to see it as a cybersecurity product, but it also integrates very tightly into the networking in the hybrid cloud. And all of this strategy is, of course, supported by our technology partners. And today we're super, super lucky to have Cisco with Christian and Jerome talking about Hypershield. And that's pretty much what I'm going to say. I'm going to hand it over to Christian, and Jerome will come after that. So Christian, please, the ball is yours.
Thank you, Lars-Erik. Thank you very much for the introduction. And let me share real quick, and let me get a confirmation that you can see the slides.
Looks good to me.
All right, thank you. So yeah, good morning, everyone, and thank you for joining the webinar, and thank you for Conscia for allowing us to present, I would say, some of the biggest innovations that we have seen for a long time in the cybersecurity space. So actually, I used to call this presentation where security meets the network and vice versa, because it's really about a solution where we kind of make the security platform come to life. So I hope you will enjoy this webinar. There's a lot of new stuff there, and I'm just going to give you a brief introduction of what is leading us in this direction at Cisco. So one of the key trends that we can see everybody is talking about is the shortage of resources and maintaining the correct level of skill sets within the cybersecurity market. Which leads to a huge problem, right? First of all, it drives us to managed services, which is good, but it also makes larger companies struggle a lot on solving even basic security functions and keeping up to date. That's why we believe that the complexity that we are facing currently when building security and network architectures, because of the change of network infrastructure, cloud adoption, application sprawl, and the dynamic of our environment, a platform is needed instead of disparate security solutions. So one of the things that will support the shortage of resource and skill is what we believe is automation. And one of the foundational pillars to drive automation, which has traditionally been extremely difficult in security, mainly because of the notion of artificial stupidity. How much do we trust AI to support automation and maybe also automated detection and response actions here? But we do believe that's a foundational pillar. So let me start with the complexity of security architectures. Those of you that goes to RSA each year understand what this slide looks like. These are some of our competitors and companions and partners in the security space. But what really happens is that the security architectures that we have built together over the last 2 decades led to these niche security solutions that we put in place to solve maybe that single threat vector or maybe that threat of the day, all promising the same, to be a silver bullet. And all these companies are doing great jobs. These tends to be very effective in their own disparate area. But what about the complexity that it gives us? That falls on the customer to try to solve, right? Which is a huge problem for us. Every time we introduce a new solution, every time we introduce a new vendor, we have to upskill our people. We need to learn to work with that vendor. We need to understand new licensing and support programs. And then what happens to our security effectiveness? How are we able to detect and respond faster if our security architecture is built upon so many different solutions that do not work together from the ground up? So this is what we call the security effectiveness gap. Every time you invest in a new security solution, you are looking at your security stack and your security operations for incremental security capability. Eventually, what you should aim for is to drive down the time to detect and the time to response, which ultimately would give you effectiveness. But what we have seen happening over the years, that the architectures that we created, it actually increased the complexity at a level where it eroded that incremental capability and just added to complexity. So when you look at detecting a threat and then trying to understand during your security operations playbooks what really happened, has the time of that increased or decreased with the level and the amount of security solutions you have in your environment? So everybody on this webinar should consider how many tools, how many systems do I have to look through to understand what a threat is doing in my environment and what is the optimal response to that particular threat, and how do I avoid it from happening again? So what we really have aimed for since, I would say, 2013 is to bridge this gap so that every time a new security solution is introduced into the architecture, it decreases time to detect and response. So that started with integrating the entire security portfolio within itself. Today, maybe manifested by Cisco XDR, but also to have open systems that understand how we can drive integration with third-party vendors. So that's why we believe that the only way is to create a platform that is tightly integrated to optimize, I would say, the people that work with the tooling and the architectures, the processes, and then the technology itself. And if we do that, then we can start to talk about automated security. But as I started leading in with, we need AI and what we call native AI to actually get to that point. And that is a journey. And some of you might, spill your coffee or even vomit when you hear AI and native AI again and again. But it's probably here to stay, and it is a foundational pillar. When we look at AI, we do it from 2 angles. One, using AI to augment existing security tools and products to make them more effective in what they are set in the world to do, whether that be a response action or whether that be detecting new threats. So simply making that security solution more effective. When we talk about native AI, AI itself is the foundation of that solution. It wouldn't work without AI, and it's based on AI to drive automation. And I just want to give you a small glimpse of the investments that we have done lately to drive, I would say, integration, automation based on AI. You can see in the top right hand corner, Armor Blocks was one of those acquisitions that gave us very strong intellectual property to augment our products with AI. Also, we have entered the identity threat detection and response area, which is a new Gartner-defined bucket of technologies that takes detection and response into the identity piece. Most companies have IAM systems, but they also have a plethora of identity sources, maybe such as a Cisco Identity Services Engine, Active Directories in various form factors, identity providers, HR systems, etc., trying to understand that hybrid environment where we have many, many identities, both from a user, machine, and even application perspective. So we've entered that market. And then to bring all that together with a single source of truth that can scale to that environment, we have acquired Splunk. And as we used to say, you cannot be the world's leading network company without security. You cannot be a security company leading without AI. And you definitely cannot be an AI company without data. And Splunk is a very important part of that, on how to structure and how to leverage data to augment even automated security. So many of you know this multi-purpose fighter aircraft. It's a Danish F-16 Fighting Falcon A model. And we have had that for a long time, even when I was in the Air Force. And we have used it up to today. Now we have supplied some of those to Ukraine, and the rest we are selling to Argentina, I believe. So what are we doing instead? Well, we're simply upgrading our defense fleet and squadrons with a new fighter aircraft. It has the same purpose, but it's just better and faster. But literally it does the same. So I would call that a next generation of something we've had even since the 70s. What we are introducing today with Jerome is not a next generation of anything that has existed before. It's a completely new way of solving existing problems that I would call basic security functions, which we are failing to succeed with due to the complexity of it without automation. Before I hand it over to Jerome, if you look at the top here, there are, I would say, 4 problem statements. With the exploits coming out, with the pace and CVEs, the amount of CVEs we see per year, the time that we have to patch before exploitation in the wild is seen is simply too high. So patching is a difficult thing to solve in a timely manner. When we look at basic firewalling to solve the right-hand corner problem of segmentation, maintaining rule sets is not only hard and complex, but it's also extremely expensive from an operational perspective. It's also, because it's usually humans writing the rules, it's also, I would say, open to mistakes, error, and failed configuration, which opens up for threats, but also compliance and audit issues. And then about maintaining the system itself. Upgrading requires maintenance windows, usually on difficult times, and it requires testing. And are we able to test in a live environment? Probably not. And most of you on this call understand that. We believe all these problems, which I call basic security functions, but are foundational to our security posture, are solvable. And with that, I would like to introduce you to my dear colleague, Jerome, and talk about how we think about solving these problems with some of the things that we've discussed. Thank you. Jerome, over to you.
Thanks, Christian. So now that Christian has set the stage of, okay, what are we doing and how does Hypershield fit into this, right? So we have a bit about an hour, and then we will spend some time on Q&A. So what will I be talking about, right? So first of all, I'll try to introduce Hypershield from a very high level and not spend too much time on it, and then we'll dive into the core technologies. Why that? Why do we do that? Because once you understand these core technologies that we actually used to build Hypershield, it will then hopefully make sense as to when we start talking about the use cases, when I will start making some pretty bold claims, but then at least you will know and have an understanding, well, these are indeed bold claims, but they're achievable, right? They are not just because I'm a TME, technical marketing engineer, because I have marketing in my title, you can expect bold claims, but I also have technical. So I should be able to justify and explain to you why these bold claims are actually achievable and not just in the far future, but achievable today. So at the end, we'll talk a bit about some of the use cases. What can you do with Hypershield? Where is the awesome power and how do you put it into play? So very quickly, what is Hypershield? Well, essentially, about a year and a half ago, some of our top leadership came to us in the security group and said, look, what if you were allowed to build a brand new product from scratch needs to be security focused, and it needs to either make things that we're able to do today a lot easier, right? To Christian's point earlier, there's this complexity gap. So either do a big step towards reducing or even eliminating this complexity gap, or this new product needs to be doing something that we couldn't do up to today, right? And they asked us, look, can you do this? What would it look like? Come up with something and let us know. And what we came up with was Hypershield. So essentially, one of the nice things with Hypershield is that we were allowed to start from scratch, meaning we were not forced to come up with some cool idea and then be forced to attach it to an existing product, right? Which automatically comes in with a whole bunch of challenges. Okay, we need to make sure that we play nice with the existing code. There's all these other components in there that still need to keep working and all of that. So we were basically given carte blanche. So what did we end up cooking up with Hypershield? Well, in the beginning, we focused on using eBPF and AI, right? And I'll dive more in those technologies to make sure you fully understand where and how we use those. But we also quickly figured out with AI, and actually like the term that Christian used earlier, artificial stupidity, if you're anything like me, and you have a security system that's AI based, and it starts and you start giving some of the control to the AI bit, why would you trust the AI bit to do the right thing, right? How do you trust the AI to do the right thing, right? For example, very often in the context of AI, what you see is the AI comes up with something and it says, I'm so much % sure, I'm 80% sure, 90, 99, 99.9. But what does that mean, right? How is that percentage point going to give you the trust that this AI thing is actually doing what's right or what's best for you in this particular scenario, right? So we quickly figured out, and for some reason my slides keep automatically skipping forward. So we quickly figured out we need to add a third big component, which is a way for the AI aspect of Hypershield to be able to gain your trust, right? Because if this system, as awesome as we can make it, is not able to gain your trust, then what's the point, right? And for that, we'll actually introduce the concept of self-qualifying updates. So what are the three core technologies that we ended up putting in Hypershield? That's eBPF. Why eBPF? Well, think of it this way, right? If we go very high level, if you want to protect something, and this something can even be a human if you're a bodyguard, right? Whatever you want to protect, you can only do a good job of protecting that thing or that human if you're as close to that as possible, right? A good bodyguard is not doing this over WebEx, right? You need to be right next to the person that you want to protect so that there is no room for any sneaky business to happen, right? Because the more distance between you and the thing that you're protecting, the more space you give to the attacker to abuse, right? So with eBPF, we'll be as close to the workload as we possibly can, right? And I'll go deep in that in a minute. Obviously, because of all the complexity and current day and age of all the tools, the complexity of the tool itself, the amount of tools, the complexity of the architecture on which our applications run and all of that, obviously, we as a human, we need help, right? So the best tool on the market available today to actually help the human deal with lots of information and or complex information are different forms of AI systems, right? Call them AI, machine learning, neural nets, all of those apply. I'll use the word AI because that seems to be fashionable today. And then, as I mentioned before, AI and eBPF are pretty awesome, but as long as that combination is not able to convince you as the end user that it's doing the right thing, we need a way for this Hypershield system to be able to convince you that it's doing the right thing. And that's where the self-qualifying updates capability is going to come into play. So with that, let's go and dive into each of these three pillars individually, and then we'll tie everything back together again with an architectural overview of Hypershield and then go into the use cases. So eBPF, what is eBPF? Well, think back to what I said in the beginning, right? If you want to protect something, you want to be as close to the thing that you're protecting as possible. Now, that means if you're trying to protect an application, that means you need to be inside the application. Obviously, that means you need to change the source code. So in this thing called reality, that's not really possible or achievable, at least in the technology landscape of today, right? So the next best thing to be is in the kernel, right? Because every application runs on a kernel. Now, being in the kernel, that means that, again, you need to change the kernel. But again, that's not easy. You need to change source code, which is not an easy thing to do. Plus, the kernel source code is probably one of the more complex pieces of software in the world today. And depending on which operating system you're talking about, if it's Linux, then okay, you have this is all open source, so you have a way of doing this yourself if you choose to do so. But in the case of Microsoft, you need to talk to Microsoft and try and get them to do it for you, right? So neither approach is very easy or even usable. So the next best thing in the context of Linux, for example, would be, okay, then how about Linux modules, right? Loadable kernel modules. Then we can go faster, but still you're touching the Linux kernel code. So that's very complex. That's not easy to do. And every time you want to make a change, you need to reload those modules. Plus, one of the downsides of using Linux modules, kernel modules, is if you make a mistake, you can crash the entire system. So you're basically doing the opposite. So even though technically it's possible, in reality, it's not that usable. So then enter eBPF. Now, eBPF is essentially a way to say, look, instead of changing the kernel, we'll just give the kernel mini programs that the kernel itself can run so that we can introduce the functionality we need. And the two advantages of doing it that way is that, one, we get access to everything that the kernel can see and do. So every syscall is now accessible to us. And at the same time, we don't need to change the kernel itself, right? Plus, we don't need to have these mini applications run in user space so that you have all the context switching and all of that. So it's very efficient. It's very nice and clean, and you can go very fast, right? Now, what's a different way of looking at eBPF? Well, again, because we're in the kernel, we basically introduce small mini programs that are usually event-driven, where you basically say, look, if something is trying to access this file, or if something is trying to do a path traversal, or if something is trying to create a socket, or if two processes are trying to communicate each other via a memory channel or whatever, essentially anything that the kernel can see, which is virtually everything, we can now see it, we can act on it, and we can control it, right? Now, what's a different way of looking at this, right? Let's try to make this real. Let's try to make this, okay, what does this mean for me, right? Remember the SSH vulnerability from a while ago, the XZ supporting library, where subnautic business was introduced. And fortunately, the industry caught it quite quickly, but still two versions of that supporting SSH supporting library were vulnerable, right? Now, what can we do if we have this eBPF capability, right? Well, you can create an eBPF program that says, look, if SSH is trying to load XZ library, and XZ library is of one of these two vulnerable versions, then either flag it or even don't allow SSH to load these libraries, right? So that's a mini eBPF program that we can create. We call it a shield in the context of Hypershield. And what that allows you to do is, well, we have access to something where before we had not, right? Because a lot of our security products are all network-based, right? They all depend on packets being sent and received and seen and all of that. But here now we introduce security controls and security concepts without a single network packet being sent and not even a network socket being created, right? This is just the SSH process spinning up, trying to load a library so that it can fully initialize, and only then at some point it will create the SSH socket, listening usually on TCP/22 and do its business, right? So we now introduce visibility and control way up the stack, right? Pretty close to the application, essentially as close as we can manage in reality today. So that's an example of why eBPF can be as cool, and hopefully that translates some of the eBPF concepts into, okay, what does this mean for me? So essentially with eBPF, we run basic programs. As I mentioned before, you can see everything, right? You can see every single user call. You can see which process is reading which file, which process is trying to change which file, what users are trying to do what sockets are being created, which process is using which socket, which already helps you for those thinking about, for example, doing policy, doing segmentation. Now we know exactly which process is talking on which ports, right? So we don't need to depend on documentation, on the developers to let us know as soon as a code update is pushed, and now all of a sudden your application is using an additional service or an additional port to do some sort of functionality. We will automatically be able to see, look, this process now also is using this socket, which is using this protocol, this port, etc. Right? So all of that information is now available. At the same time, to Christian's point earlier, that essentially means that if you take an inventory of all the data points that your entire security portfolio that you happen to use is generating, now you add to that every single kernel capability now also becomes a data point. and it becomes a time series data point, right? Because these things will change over time. New processes will be spin up, spin down. So essentially, the amount of data points that you as a security admin, on the one hand, have access to, but on the other hand, also need to make sense of, is exploding, right? So, which again leads into later on the AI bit, because as a human, we will suffer. We will suffer even more if we dump all of these data points into your realm of visibility, and you need to have a way of dealing with that, right? Now, a final thing that I want to perhaps highlight in regards of eBPF is two things. One, because it's running in, natively in the kernel, speed is going to be excellent. The performance is going to be very good. And yes, I have marketing in my title, so why should you believe me, right? Well, think of it this way, right? To try and show that, one, this eBPF technology is mature and fast, there's almost no packet you can send to and from Meta or Facebook that is not seen and processed by eBPF technology, right? Which should instill some level of trust that, look, this technology works and it's fast, right? Otherwise, hyperscalers like Meta, like Facebook, and many others would not be using it. On the other hand, and this is important for those of you in the architectural role and in the design role, eBPF is what provides Hypershield its superpowers. Why is it important to remember this? That's because when we then start talking about the Hypershield architecture and we start talking about the eBPF data insertion points and also the Hypershield VM, is that without eBPF data points and eBPF agents generating and inventorizing and seeing all of these applications, what they do and where they are, there is little information that Hypershield will have to put in the VM, right? So just using the VM but not the agent is not going to make sense, or little sense, right? So then you might think of, well, eBPF, it has been around for over a decade. So why now, right? So why has nobody done this before? So why is Cisco now all of a sudden coming up with this, and has nobody else done this? Well, obviously there's plenty of smart people out in the world, and not all of them work for Cisco. So Isovalent was one of those companies that a few years ago was established to actually use eBPF to the benefit of the IT industry and mainly in the security area, right? So they have 3 products: Hubble for observability, Tetragon for security, and Cilium for networking. And we acquired it about half a year ago, and now we're working closely with them to actually use all of this eBPF awesomeness in the best way possible as part of Hypershield. So, Christian, any interesting questions I should touch on now before we move on to the next section?
No, I think you're good to go. Go continue.
Okay. So the AI bit, it's kind of self-explanatory why we need it. I'll still touch on it for a bit, but let's perhaps focus now a bit on the self-qualifying updates bit, which is the system which hopefully will allow Hypershield to gain your trust, right? And when we talk about self-qualifying updates, it can mean many different things, right? It can mean in the context of software upgrades, right? We want to update, we want to apply a patch, we want to go to a new version of the code. Any type of code upgrade falls into this bucket, but also policies, right? We want to change the rule set, we want to make changes to the rules, we want to introduce additional shields, right? Think of shields as small eBPF programs here and there. Anytime you introduce a change, you need to do a whole bunch of work, right? You need to make sure that the change, first of all, is needed, that the change is the right change for what you're trying to achieve. And then you need to start testing this first in a lab environment, then in staging environment, and gradually you build up your trust in this change that it will not break anything. And then at some point, somebody is going to be brave enough to actually go and deploy this in production, and then pray to the gods that nothing will break, right? This is a very challenging, complex, and difficult and time-consuming process. So what we're trying to do here is take virtually all of that and make it an integral part out of the box of this product, right? To Christian's point earlier, is not to remove the complexity gap, but to remove it altogether, right? Because everything is fully automated, we will do all of the necessary checks and validations. And at the end, instead of giving you like a percentage, I'm so much % sure, we say, look, I am very sure that this is going to be working, and this is why, right? We need to give the AI and all the automation a system to explain itself to you, and not just explain itself to you, but also show you that it has already tested this in your live environment. And now you might get very nervous, right? Wait a minute, did I just say we will be testing in your live environment? Yes, I did. but in a way that you should feel comfortable. So how is this? How do we do this? We introduce the concept of a second data plane. So of course, any product that is processing data, packets, looking at events, CMs, anything, they have a concept that they call data plane, which is where all the action is actually happening, right? Now, what we simply do, because in essence, the self-qualifying update process is a very simple thing, but it's very powerful in what it can do. So by creating a second data plane, we call it the shadow data plane. This data plane will see the exact same thing that the primary data plane is seeing. And what we can then do is install the new software version into this shadow data plane and see how it behaves, right? So one cool thing to know about the shadow data plane is there is an implicit don't do anything action at the end of the pipeline, right? Where the primary data plane at the end, the action is, okay, do whatever the policy says you should do, or do whatever the software code says that you should be doing next. With the shadow, we just record what we would do, right? So we then make no changes. There is no impact. There is no, this is not an additional step in the processing sequentially. So it's just running in parallel. And we just play pretend, right? What if this software was deployed? How would it work? And then we start looking at a whole bunch of metrics, right? So for example, once we deploy a new version in the shadow, we start checking things, right? Automatically testing things that you probably test as well, but you would not test it in production because you don't have the tools and the capabilities to actually do that without influencing your production environment. But here, by introducing the shadow data plane, we can do this in live environment without the risk of interrupting or influencing anything. And then we start checking things, right? So the usual suspects, the obviously one are, okay, is the CPU level similar between the two versions, right? If this is a minor patch, or if we introduce a big new feature, then obviously some change is expected, but we will check, okay, what is the actual difference? Is it within the realm of what we expect it to be? The same for all the other usual suspects, right? Memory, we will look at latency, we will look at how we process packets. Do we do the same action with different packets? Are they, is the end result still the same? And a whole bunch of additional things, right? I think at this point in time, we're already over 100 different things that we actually go and test, other than these very obvious ones. And then at the end, what we do is we generate a report that says, look, this is what would happen if you deploy it. So instead of deploying and then praying to the gods that everything will work as it's expected, or that it will work the same in production environment as it did in your lab and your staging environments, now you know exactly what would happen, right? And we give you a report. Look, this is what it would do. This is the difference in packet processing behavior. This is the difference in delay, difference in CPU, memory, etc., etc. So for example, if we do a CPU optimization patch where we say, look, we actually improved and we made our processing more efficient, that you would actually be able to see, yes, indeed, we see that in the shadow data plane version 2.1 is actually consuming less CPU to do the same thing, right? And you would know. And you would know, and everything which makes your environment unique, right? The hardware footprint, the traffic footprint, the application footprint, all of that in a report. So yes, we might still do some form of percentage of or some verbiage and words like how sure we are, but we would immediately back it up with like, look, and this is why we are 90% sure or 99, and or why we say, look, actually there might be an issue with this version. We don't deploy it. This is the difference that we saw, or this is the metric that we measured that is a reason for concern for us to double check that everything is actually fine, or there might be an issue. And the cool thing with all of that is that in case there is an issue detected, it's not like with some other products that you then have like a button, do you want to raise a attack case or this or that? All of that is, we automatically file a bug. And actually, and this is actually something that I asked for 10 years ago when I was a tech engineer, we will file 2 bugs. One, obviously the bug with the issue that needs to be investigated, and 2, a bug against our own QA controls, right, inside Cisco, because obviously we do a whole bunch of validation and testing and quality control ourselves, but every time a potential issue is detected, we will also file a bug against our own internal QA, so that this type of issue is never found in customer environment ever again, right? We will always catch it ourselves next time. And obviously the same applies for policies as well, right? And then once we are that you're okay, you review the test report, you did whatever additional due diligence to figure out, look, I'm actually happy with this new version or not. Then you can just say, okay, we will actually apply the upgrade, or we will do the update. But what does that mean? Well, the only thing that this means is to the primary data plane that was running the 2.0 version, you now say, well, instead of doing as action what the code says, it now becomes an implicit don't do anything. And to your shadow data plane, you now say, instead of doing an implicit don't do anything, we will now start enforcing or doing the actual action that this piece of code actually would tell you to do, right? So there's no new deploying of code, there is no nothing of that. So even doing the update itself is going to be made a lot more streamlined and simple to do. And then obviously I was giving the example with a software upgrade, but the exact same reasoning applies to policy change, right? Or testing a new shield or a new eBPF thing. So you can have, for example, you want to add a rule to your policy base, but when talking to some customers have a policy of hundreds of thousands of rules, right? And then, yes, you can have all kinds of scripting, and even now within some of the security products, we start introducing concepts like AI ops, where we have all kinds of smart computing that will actually go and validate. If you introduce a new rule, well, perhaps you don't need to add the rule, right? Your policy already is doing exactly what this rule says. Or you might see, look, if I want to introduce this rule, I actually have a conflict. If you want to add a rule that says permit from A to B, but somewhere in your policy, you might have deny A to B. So there's a conflict. So it would automatically detect that. Or that you say, well, actually, if you add this rule, you don't really need it because it's a shadow or it's already an overlap with an existing rule, right? But more than that, we can now also apply the policy to the traffic in the shadow data plane, so it's not going to interfere with anything. And we will see, look, is this actually behaving the way you want to? So for example, if you introduce a rule to no longer allow HTTP traffic on TCP port 80, then you can see by comparing the deployed policy with the new policy that in the current traffic, you actually see TCP 80 going through, but in the other, in the new policy, you see the exact same traffic allowed except TCP 80. Now TCP 80 is absent, but nothing else is absent, right? So that again, and this is obviously a very simple example, but then you will have a report that exactly qualifies and shows you, look, this is how your new version of the policy would behave if you would have deployed it in this particular place of your network, right? So again, testing on the actual traffic in your actual environment with everything which makes that environment unique. And I've not seen many customers where their staging environment is even remotely close in resemblance to the production network, right? Simply because of the volume of traffic, the diversity of applications running in the staging network and all of those things. And those will have an impact into cause a difference between your staging environment and your production environment. So again, end result of the shadow data plane, we give a detailed report where we scan and measure the difference in metrics between the actual policy and the new policy that you're trying to deploy, and then do as much calculation as possible to figure out, look, the differences that we see in all these different metrics and data points that we test and compare against, lead us to a conclusion of, yes, we trust this proposed change, or now we detect some issues that we think you should take a look at before actually going and deploying this new policy, right? So all of this as a tool to enable the AI to convince you as an end user, well, yes, whatever this AI system of Hypershield is proposing, you actually feel okay with this. Now, again, and this is not going to be new for many of you, why AI? Well, complexity is on a whole bunch of levels, right? So the complexity is on the platforms on which your applications run. The complexity is in the amount of CVEs detected, right? And known CVEs, right? For example, a very simple question, if you're like the head of security of any customer or any department, a very reasonable question to ask would be, look, given all the applications that are currently running in our environment, how many known CVEs do we not have protection against? A very reasonable question to ask, right? Because you should know which applications you have in your environment. You have access to these public databases with all these CVEs. So you should be able to match the two together and figure out, look, these are the CVEs that we're currently vulnerable to, right? Because in theory, you have access to all the information you need to answer this question. However, in reality, that's not necessarily the case, right? I don't know many customers that feel very confident and that are able to say, look, I know exactly which known CVEs we're vulnerable against, and I know exactly how to patch those, right? Very few are able to do that. But it's a very meaningful question to ask, right? And if you want to be good at securing your environment, you should be able to answer this question in near real time, and you should have a way of in near real time when a new CVE is published to come up with a way to actually deal with that. Another reason for AI, and again, this is most likely nothing new to any of you, is the complexity of a single attack vector, right? It's no longer a simple thing. It's usually a sequence of events. Each of these additional individual things might be quite difficult for you to understand given your knowledge, right? Because not everybody is fluent in kernel technology and networking mechanisms and encryption mechanisms and path traverses and all these different attack vectors. If you want to come up with a way to protect against that, you kind of need to understand this and know how they work before you can protect against it, right? Unless you, again, depend on a tool, one of the many tools in your security portfolio, or you have a little helper, right? And this AI little helper, as good as it can be about claiming that we can enforce and we can apply all of these things, you actually need to have the AI, you need to give the AI a way to actually build and earn the trust, right? And not once it's there, to keep verifying that whatever trust you put in certain actions that the AI take, that you can keep trusting them, right? And that's an integral part of Hypershield, right? So it's never about so much percent sure. No, we will always do a whole bunch of different things. And let me skip ahead to an example of what this could potentially look like. It is, well, the AI detects something and wants you to do something, right? It tries to make a policy push. It will always say, look, why am I bothering you? What is the reason that all of a sudden I want to propose a new policy, a new eBPF script, a new something, a new shield, right? So it's always going to say you why. Then it's going to say, look, this is what I'm proposing. And this is where we introduce the policy engine that is very similar to what AWS released a while ago, Cedar based, right? We will have a principle, which is your source, your resource, which is essentially your destination. The action is what is the source trying to do with the destination. So easy example, you want to read a web page. The principle might be your phone. The resource is facebook.com, and the action is, okay, log into this page or read this page or do a post, right? And that's essentially the bare minimum of a rule. Now, there's two additional things. The condition can be, for example, to the SSH example that I gave before, where the principle is the SSH process, the resource is the XZ library, the action is load library, and then you can add a condition that says, look, this rule is only going to apply if the library that we're trying to load is of version X or Y. And then effect is, okay, once we have a match for the rule, what are we going to do with it? Are we going to log this? Are we going to flag this? Are we going to deny it? Or are we going to allow and flag it or anything like that, right? So that's essentially what the Hypershield policy is going to look like. So effect, principle, action, resource, condition, all of that is found again. And then you will find a way, look, we actually have, we found alternative remediations, alternative shields for this exact CVE, but the one that we suggest is the one that we think has the highest probability of being the best one for your particular environment, with everything makes your environment unique, right? And then one thing that I actually asked for, currently the test report is hidden behind those three dots. I want to make it as obvious as possible for you to get access to the actual test report that said, look, while testing in the shadow data plane, this would be the exact behavior if you would have deployed this, right? So that again, instead of just recommended and yes, we think this is best, especially in the beginning, I would not anticipate any single one to actually out of the box trust Hypershield and the AI that we have, right? Why would you? You need to have a way to start trusting it, to build the trust with this system, to figure out, look, every time it comes up with a remediation, you actually go and accept this, right? It's the exact same thing with humans, right? If you have a new hire in your team, he can be a senior distinguished engineer, or he can be straight out of college. In the beginning, you will always kind of double check whenever he's proposing or doing something, is this guy living up to what he's supposed to be able to do, right? You will always have some level of checking before you actually start trusting him. And obviously with a distinguished engineer versus a new hire, the amount of time between you get to the point where you fully trust him is going to be different. It's going to be the same with this system, right? But we really worked hard on giving this system the tools and capabilities to earn your trust, right? It's not just us as Cisco asking, yes, we are Cisco, and because we are Cisco, you should trust us. No, we will give the tool all the tools and capabilities to earn the trust, right? So again, a different view on this. So you have the why, the what are we doing? Do we have alternatives? And why do we actually bother with letting you know that there are alternatives? The simple reason for that is, as a human, you will always have some angles of knowledge, intelligence, or things that you just know out of experience that the AI either is not able to know, or the AI is not good enough to know, or does not have enough intricate knowledge about everything which makes your environment unique, so that we still give the human the chance that, for example, yeah, but we are not doing this a certain way because that will break something else, or we're doing this because we're anticipating something that will happen in the future, right? Which obviously the AI has no way of knowing. So that's why if we come up with alternatives to still try and protect against the vulnerability in a different way, we'll still let the human have access to that, so that they can actually take all the knowledge and experience that they have to say, well, I actually know that this is probably not the right way of doing. Let's take a look at the alternatives to see if there's one in there that actually makes sense for whatever makes your environment unique. Cool. So with that, I think I've covered the key 3 ingredients of what technology does Hypershield use. Christian, Lars-Erik, any questions you want me to deal with before we move on?
Actually, we have no questions so far, so everything must be clear.
Either I'm making a lot of sense, which would be a surprise because I just came out of PTO, or you guys haven't found the QA button yet. So do feel free to ask questions in there. As you've noticed, we'll try and make some time during the session today. If there's questions that we cannot answer, there will be a follow-up coming with all the answers in detail. So don't hesitate to post questions in the Q&A box. Okay, so now that we talked about what technology did we put into Hypershield, what does it look like, right? So if you buy a Hypershield, what did you get? What do you get? If you buy from Cisco a box with Hypershield inside, you open the box, what's inside, right? Well, first of all, it is CDO driven. So Cisco Defense Orchestrator, that's the SaaS platform. That is where the management and part of the control plane will live, right? So from there, that's where you are going to interact with. So if you configure and set up the system, you do all of that by logging into CDO, Cisco Defense Orchestrator, and from there you have access to everything that you need to do. Obviously, that's not the only bit, right? You actually need the bits with the eBPF, with the shadow data plane and all of those things. So ideally, what we want is have eBPF access to eBPF capable operating systems in as many places as possible, right? Because you will have applications running on a diverse footprint on Microsoft, on Linux. You will have some IoT, some OT boxes, and all of that. So obviously, with Linux, we're good to go, right? As long as you have a reason enough kernel where all the eBPF capabilities that you need are there, we can start using. Now, the way that we then interface with that operating system is usually through a shim, an agent, whatever you want to call it. But then I already see server guys and application guys roll their eyes and scream like, no, not another agent. And usually they would be right. Usually they would have very good reasons to say no to us proposing an agent. But let's take a look, right? Because on the one hand, we have this thing called eBPF. And on the other hand, what are the usual reasons, valid reasons, to not want an agent? Well, you don't know how that agent is going to behave, right? You don't, how do you make sure that that agent is not going to starve existing applications from CPU and memory and other resources, right? How do you make sure that this agent is going to behave? That's a big concern. The other concern is for every agent that you introduce to your environment, that's another thing that you need to lifecycle manage. And these 2 concerns are usually the main 2 concerns for people to be reluctant to agents. On the other hand, with eBPF, we now have all the capabilities to ideally put all the guardrails into place saying what this can do, right? What the agent is allowed to do, how much CPU is it allowed to do, on which cores is it allowed to run, and all of those things. So all those guardrails that you might need, we now have access to the technology to enforce those. On the other hand, the lifecycle management, again, we talked about in depth about self-qualifying updates, that should kind of take most, if not all of that heartache away, right? Especially because I have a single control plane for this distributed system. From a single point, you can actually go and see whenever a new version is available. No need to download software artifacts, no need to qualify and test them and do all of that. It will automatically be tested, and you will have get an update when a new version is available that is fully tested and approved and validated to be okay in your specific environment. So that the only thing that you need to do is read the report, decide if you agree with it or not. If you agree with it, the only remaining thing for you to do is to figure out at which point in time you want to apply the update, at which point it's just going to be a swap from the shadow to the primary data plane, essentially, and it's pretty much done, right? So those 2 key reasons are like friction points to use an agent should be not entirely, but almost completely be removed. And that agent is going to be doing many things, right? So that agent is not just going to be a way to give a secure channel between Hypershield control plane and each of the agents to talk and deploy these eBPF scripts, but it can also do a few other things, right? There will be some local AI data algorithms that will be running where it makes sense, right? Because another thing that we need is inside of this global control plane, we will have a huge amount of very dedicated AI ML compute backend where we can actually do near real-time computations on all of these data points that we now have access to. However, we need to filter out what do we actually send to the mothership for two reasons. One, we can't dump all of the information in there, right? Because that would be too much. So we need a smart way to filter out, okay, which data points actually would help us to do things like correlation across different operating systems, etc. And on the other hand, we also need to put in a control into place for those customers that want to have control over what data is actually sent back to the mothership, right? Because they might have privacy reasons why they said, look, I don't want this data to go into the Cisco clouds, right? For whatever reason, or even for legal reasons, right? They need to comply to local legislation that says, look, this is how you can or cannot treat personal identifiable information, people information, healthcare information, and things like that. So there might not just trust issues, but also like legal issues that we need to make sure that our system can comply to. And then for the Microsoft question, what about Microsoft, right? There is no eBPF there. Well, there is eBPF in Microsoft. It exists, but it's not a default part of the operating system when you deploy Microsoft. However, we've been talking with Microsoft and they're actually working very hard to actually make that a default option or to add it by default with the operating system so you can actually start using it, right? You might have seen some security incidents in the past few weeks, months, where there is some talk that, look, eBPF would have made eBPF in Windows and Microsoft would have allowed us to deal with it differently than we were able to today. So it's not a matter of building eBPF in Microsoft. It's not a matter of convincing Microsoft. It exists. It's a packaging effort, and they're actually doing it right now. Timelines are in the next few months. It should start to become available. But again, we'll need to see exactly when and how that becomes available. But it's coming soon, right? So that's Microsoft and the Linux operating systems explained. But then there still might be places where we don't have access to eBPF, right? Either because the eBPF capability is not in the operating system where your application ends up being running, or you might not have access to the operating system to actually go and start using the eBPF capability, or it might be an IoT or an OT device where, again, you don't have access to whatever is running inside the device, but you still want to provide some layer of protection, right? So to that effect, we also have the form factor of a virtual machine, and that virtual machine is mainly going to be an enforcement point. Right. So the key thing, remember when I talked about eBPF, when I was addressing the architects and the designers amongst you, eBPF is what gives superpowers. If you only deploy the Hypershield VMs, but you never ever or don't anywhere deploy any of the agents to give access to the eBPF capability, then those enforcement VMs will not really have a good idea of what to do, right? Because most of, if not all of the clues and information and data points that the system acts upon all come from eBPF agents, right? So it's a good thing to remember that yes, the VM exists, the VM form factor exists, but it is just an enforcement point of the bigger system, which is Hypershield. So we already explained a bit the CEDAR-inspired way we build our policy, right? Because obviously now that we have access to we can see and control things even before a network socket is even created. Obviously, access list is not going to cut it, right? With the access list rules and policy rules that we have there, there's no way that you can say, look, if SSH process is trying to load XD library of version X and Y, with an access list, that doesn't work, right? So we had to change the way we define a policy, right? Now, again, to Christian's point, yes, we could create our own policy network and again, policy model. And again, complexity through the roof for you. It's not just learning a new product, but now you also need to learn a new policy model and all of that. So again, all making your life more difficult, where the goal we set out was to make your life easier and more efficient. So we used an open policy model, an existing policy model, and one that we know was able to do what we needed to at scale, right? So That's why we used the AWS Cedar approach to actually go and define our policy. Now, at the same time, one thing that I didn't mention yet is that Hypershield is fully API first. So yes, we have a web-based UI through Cisco Defense Orchestrator, but every single thing you can do is also exposed through the API. And some of our actually early access customers, they don't care too much about the UI at all, right? Because they see this as a new way of enforcing security and doing things, and they are going to fully insert this into whatever automation pipeline that they already have, right? So they don't care too about the UI whatsoever. They just want to use all these capabilities in whatever automation pipelines they already have or that they're building out right now, right? So everything is API first. Everything that you can do is also possible through the API. So if you then take a very high level view of, okay, yes, question.
Before you go on, there's a question coming in. So I think this is a conceptual understanding that you can clarify quite quick. The question is new hardware needed to support the shadow data plane?
No.
Does it use resources from the current data plane, or is it a virtualized data plane?
Yes.
If it's run in CPU memory, but then it would not be a true shadow of the physical data plane. So maybe you can clarify the architecture of the software. Yeah.
So good question. So and it's going to be hard to explain the question without going into some implementation detail. So I'll try to find the middle ground. So the way that the shadow data plane works, first of all, everything is software only. So everything I've defined so far is pure software running on generic CPUs, right? So you don't need specific hardware to be able to use Hypershield. Now, to the second part of the question, okay, then for this dual data plane, if you have a second data plane running somewhere on the CPU, it's going to be a different process, right? So it's going to be a different process ID, so it's not going to be exactly the same. However, it's going to get the same inputs. So it's going to be a second process, which is the shadow versus another process, which is the primary data plane. But the inputs are going to be exactly the same. And then you might say, well, this is going to be very CPU costly, right? But not necessarily. For example, let's give the example of processing a packet, right? We don't need to duplicate the packet, right? We just give a pointer to where the packet exists in memory to both of these processes. And they both use the pointer to figure out, okay, where is this packet? How can I go and read it and figure out everything I want to do? And then the difference is going to be, for example, if we are about to do net address translation, the primary data plane would actually go in and make the change. The secondary, the shadow data plane is essentially going to log, look, these are the changes I would make to the packet. And instead of doing them, they would just log it. So then at the end of the testing period, we can then compare, look, this is what was done, and this is what the shadow would have done. Compare the changes to make sure that the right changes are there or not there, right? Now then, as far as if you introduce the shadow data plane concept, this is going to be an increase in resource consumption, and then mainly CPU. Yes. But again, we have two data points that might be of interest. The amount of CPU is in the percentages, so a few percent only for the entirety of the Hypershield agent and the testing. And the second thing is we can even put rules into place like we only use maximum of up to X% of free CPU. So not an absolute number of like 5% of CPU gone. No, you can say, look, we will use 2 or 3% of the free CPU, so that whenever, for example, you just and I actually was talking to a customer that was exactly like that. They were like a governmental agency, and they said, look, at some point throughout their entire cluster, once a month we run this huge, very CPU intensive computations, and actually it is so optimized, this application, that if we stop running it on a sibling or on a core, so because Hypershield wants to start running there for X amount of milliseconds, it will have it will degrade the overall performance of this high density computation by a lot, right? But because we only use X% of free CPU time, if there is no free CPU time, there is no risk of running the of Hypershield starting to run, right? And again, you can control this and configure this in detail with the eBPF capabilities, right? To make sure that we put the guardrails into place as to, okay, what is Hypershield allowed to consume resource-wise, and are there even limitations or like a temporary limitation that you want to be able to put in place? So at GA, I don't think we will have fine-grained control exposed to the end user as to what are these guardrails, but we will have some default guardrails into place to avoid Hypershield consuming more resources than makes sense, or even interfering with the application, right? Because in the end, that's the last thing you want to do is interfere with the application, because we're trying to do the opposite, right? We're trying to protect the workload. So I hope that answers the question. Cool. So then we'll finish up like the architecture and the overview with a high level like positioning. So where does this fit both as a solution as capability today? So we have the management and part of the control plane in CDO, and the two main use cases that we're going after at as we are launching Hypershield today are exploit protection and autonomous segmentation, and we'll dive a bit more in these two use cases next. But obviously, and any of you that have played with eBPF already generically, or even as part of using some of the tools and capabilities that Isovalent has, or even other vendors that are using eBPF, this is just the beginning, right? These are like the two top of mind use cases for most of the customers that we talk to, but there's going to be lots of additional stuff coming in the future as well, right? So this distributed exploit protection and segmentation, those are the two things that we're going after. Now, one thing about the hardware, right? So especially given the question that we had and some of the statements that were made in the early launch videos of Hypershield a few months ago, especially in the context of like Hypershield switches, DPUs, and all of that, right? So how does dedicated hardware come into the picture? Well, first of all, to the point of, yes, the agent and the testing and the dual data plane, they all consume a certain finite amount of CPU resources, right? And given that more and more servers these days, they come equipped with DPU and or GPU, especially the DPU, we can actually make a very interesting use of those DPUs, right? First of all, most DPUs, they have a bunch of generic CPU cores, usually ARM cores or something similar anyway. So what you could do is you could run the agent there instead of inside of the generic CPU of the host operating system, again, to minimize the impact of Hypershield onto your application environment. The second thing with those DPUs is we can then also start using some of those true DPU specific chips and hardware capabilities to start doing certain things, right? Some of the AI computations and some of the other stuff. So DPU support is coming in a few months from now as well. And obviously DPU support will be dependent on the DPU. So it will not be a checkbook for DPU support, and whatever DPU you choose will be supported. So it will be specifically for certain AMD Pensando and NVIDIA Bluefield DPUs. That's the one thing that's coming. On the other hand, to try and avoid the questions regarding, okay, what about a Hypershield in the switch ports, right? So there was at some point mention of every switch port will become a Hypershield enforcement point. That is also coming. That's a bit further down the road, because there's a few dependencies that all need to fall into place. And there, the goal or the concept is, again, something similar of using DPU resources inside of a switch, first of all. And then second of all, to use like, you can consider it like a new form factor of the enforcement VM, but then instead of this enforcement point being a VM, it's going to be a small piece of code running inside DPU resources inside of a switch that would essentially transform every switch port into a Hypershield enforcement point, right? Now, again, for those of you that are in the architecture and designer role, key thing to realize is that the intelligence comes from eBPF, right? So even though, yes, we have eBPF capable operating system running inside of the switch, but it's not because there is eBPF there that we can do what you would think you can do with eBPF there, right? Because we want eBPF in the kernel where the application is running, but the application is not running in the operating system of the switch, right? It's not running on Catalyst OS, it's not running on the Nexus OS, it's running on your Linux, on your Microsoft, on inside of your VMs, on whatever virtualization infrastructure that you have, right? So the key thing to realize is as far, and this again, this is a few quarters out, right? At least these eBPF or these Hypershield enabled switch and physical networking infrastructure, it's going to be the enforcement aspect. It's not going to be the intelligence aspect that's going to be happening there, right? Cool. So next up, we'll spend some time talking about, first of all, distributed vulnerability protection, right? This is all about, like I mentioned in the beginning, right? The link between knowing what application is running where, like a near real-time inventory view of what applications do you have and where are they, combined with a real-time link to all of these public CVE databases, to then in near real-time figure out, look, this is the full list of CVEs which are currently open in your environment, and what to do about them, right? So if you look at things with from a vulnerability point of view, one thing is figuring out which vulnerabilities you need to patch, right? Which is already a non-trivial thing. Yes, in theory, you have access to all the information, data points that you need to figure out what are my open vulnerabilities. But again, this thing called reality teaches us a different lesson, right? It's way harder than ideally it should be. So that is one of the key things that we're trying to address with Hypershield, right? We want to get to the point where you have a near real-time inventory view of what application and what version and what libraries are running where, what are the known vulnerabilities, and how can we provide shields against those. And that's one major aspect, but the other major aspect is this shields thing, right? Because if you look, what if we just gave you the list of CVEs that are applicable in your environment? If that's where we would have stopped, that basically means you then need to start talking to each of those application teams. You need to tell them, look, this is a reason that you need to go patch as soon as possible. But first of all, the patch might not even be available. Not every CVE out there today has, for software, has that software having available patches to actually mitigate that vulnerability, right? Especially for recent CVEs that were exposed where the researcher or the attacker finding it is not doing or not giving the vendor of the application enough time to actually become aware of it and come up with a fix, so that when they announce the CVE, they can immediately say, look, and this is how you fix it, right? That's one thing. But the other thing is, doing a software update is not just you download the patch and you apply the patch, right? As usual, you need to do some qualification, you need to test, you need to make sure it's not going to break anything. So all of this testing and validation needs to be done before you can actually go and apply the fix. And even something as crucial as the log4j, which is what, a few years that we are aware of it, the amount of systems that are still vulnerable to log4j, it's amazing, right? It's mind-boggling. And it's not because people are lazy or people are not aware of it. It's just the complexity they are forced to deal with before they can actually go and patch the system is too much. So this is the second big thing with our vulnerability protection and Hypershield, is that we can say, look, we will deploy a shield immediately or as soon as the admin actually reviews the AI generated shield and approves it, so that you're protected, right? Which is different from patched, right? So with the example with the SSH vulnerability and XZ library, right? We can immediately put a shield that would avoid or would prevent the SSH process from loading the library if it's one of those two vulnerable versions. So that means, look, you're no longer vulnerable, but your operating system guys or your software guys still need to do their piece of the puzzle to make sure that those two vulnerable XZ libraries are not present anywhere, right? So essentially what this, with what Hypershield allows you to do is you can in near real time protect your environment to not be vulnerable against those CVEs. And at the same time, you give your application team breathing room. You give them the time and space to actually do their prep work for the final patch at their own rate, giving them the time without the pressure of, as long as you haven't patched it, we're vulnerable. That is now gone, right? You're protected, and your applications team still needs to do the patch, right? So that it's no longer running vulnerable code, but you're no longer under the gun, right? You're protected, the CVE is not exploitable, and your application team has all the time they need to do their work properly without having to rush it, without having to, and we all know what happens if you need to rush things, right? So it's all about making sure that we put the balance of time and effort in our favor, right? So yes, as soon as a vulnerability is detected, we can almost immediately come up with a shield to protect you against it, so that you're not bothered or not, you don't need to force your software guys, your server guys, your operating system guys to force patches down their throats and have them do it as soon as possible, because more often than not, doing a rush job introduces more issues than it would solve, right? So those are the two key aspects that we're trying to do with Hypershield and in the context of vulnerability protection. Now, one thing that we're going towards is, and taking a step back, is about writing policy, right? That's an easy example to give, especially in the world of traditional firewalls, right? It's all about writing policy. Somebody needs to make policy changes, policy changes all the time. Now, if you look at the amount of time and effort it takes to write an update for your policy, right? Not even thinking about all of the tools and time and effort it takes to, once you figure out what the policy change is going to be, to actually then go and deploy it, not even thinking about that. That's a lot of time and effort spent by a human, right? And if you then take a look at all of the amount of time it takes you, a human, to write some policy, if you then take a look at this human of this seniority level spending so much time on this policy update, how efficient is his use of time versus increasing the security of your environment, right? That's essentially what you want to do from an operations point of view, right? You want to maximize the efficiency of the people working on securing your environment. So first of all, how would you measure this? How would you know if they're efficient or not? How would you know? So one of the things that we are trying to aim for with Hypershield is that we want to go away from making manual policy changes towards, you will have your AI assistant, your AI helper, coming up with all the changes in response to all of the known CVEs, and then the human can just check, is the AI system doing the right job, right? And not only that, once we have an inventory and once we have a list of all the CVEs, we will make a prioritized list. So obviously, we will start with the high risk CVEs first, combined, and not just the high risk, but also if you have like a CVSS of 10 and then a CVS of 9 vulnerability, but for the CVSS 10, you only have one small application running somewhere, but for the CVS 9, you have a huge amount of very important applications running, then we might prioritize that higher than the CVS 10, simply because of the impact of securing against that particular CVE on your environment would be way higher than dealing with the CVS 10 before, right? So even that prioritization of work, we will do for you in the context of Hypershield. And then even one step further, over time, you can then have like a view where over time you can see, look, at this point in time, we were vulnerable, these vulnerabilities were open. Then as soon as we detected this, our admins, in a matter of minutes, they actually reviewed and deployed the shield. So you can nicely see, and over time, what is the overall security posture of your environment, right? So just that on its own, I think, is already pretty cool. So the type of work that the human operators would be doing, in my mind, is getting way more interesting, right? Because they get to evaluate the CVEs, that they would be notified where they are, where the applications are that are vulnerable against them, and they can actually go and verify that whatever shields that Hypershield is proposing make sense, and they can then also have a very detailed view and report that they can give to, for example, security leadership, that's saying, look, I've spent half a day this morning on securing our environment, and this is the impact of me spending half a day reviewing shields from Hypershield, right? This is the amount of vulnerable applications we had this morning, and when I went to lunch, this is the current posture of our environment, right? So it's not just for the security team, but also if you're like a partner or a managed security service offering a type of company, it makes it very easy to actually show to your end customer, look, this is the impact of me spending this amount of money on deploying Hypershield and this amount of times actually using Hypershield, and you can show exactly, look, this is the impact we will have on the overall security of your environment. Cool. And then that's what I said. I'm going to be making some claims that might be seeming very bold, and you might immediately say, "Oh, this is the sales guy, this is the marketing guy trying to pitch this latest fancy thing." We also have ways to now deal with unknown vulnerabilities, right? And that's a big one, right? So yes, if you have a detailed inventory of all the software, including versions and where they run, and you have access to CVE databases, you can create some not super advanced, but still reasonably advanced code to actually compare in near real time and figure out, okay, these are your known open vulnerabilities. But we can also detect unknown vulnerabilities. And how is that? Well, keep in mind our eBPF superpower, right? What if you see a new process spun up that you've never seen before? What if you then see that process rewrite every single file on your file system? And what if every single file after it has been rewritten has a huge amount of entropy, right? Those are three things that you can detect. And what type of process does this? Well, an encryption process. What is an encryption process? In this day and age, usually it's one of two things. It's disk encryption software that you installed to actually encrypt your data file systems to make it more secure, or it's ransomware, right? And ransomware, if you remember in my slide where I had like this huge attack vector pathway going from this to file traversal to privilege escalation so you get closer and closer to the point where you can actually install a process that will then start encrypting everything. Detecting this final step and then blocking this process as soon as we start seeing it, that it starts encrypting files, is actually a way to actually detect something that resembles a malware before we actually let it run rampant through your network, right? Or run rampant through your systems. So that's one way of making an example of what you can do, right? You can, for example, generalize certain CVEs. So for example, if we look at some of the CVEs, we can do the same thing that the human brain does when it's learning something, right? Especially children, how do they learn, right? If they put their finger in the flame of a candle, they will burn, it will hurt, and they will do two things. They will learn that if I put my finger into the flame of the candle, it will hurt. But the human brain also does something very cool, and that is a generalization step. It will generalize the thing that, look, a flame hurts, so that then if they go, for example, to a barbecue fire or a log fire or whatever, they will also see that this is a different type of flame, but it's still a flame. And so they generalize the candle to flame, and then from flame to whatever fire that they might or might not encounter, and realize, look, this is most likely also going to hurt if I go too near, so I will not go near. Because we also have AI systems parsing all of the data points that we now have access to because of eBPF, we can do similar things, right? We can process known CVEs, we can generalize them, and then we can try and detect different flavors of existingly or known bad behavior, right? So it's not just the known CVEs, it's also unknown vulnerability protection. And again, this is also something where over time, as we start deploying Hypershield in the real world, we will learn if and how good our system is at detecting those, right? How would we detect this? Well, if Hypershield starts filing new CVEs, right? Because obviously, if it finds something that was not detected before and we figure out that this is most likely the malicious, we will double check it. And if it indeed turns out to be malicious, you will start to see Hypershield create CVEs and deploy them, right? So that would be a good thing to keep in mind in the future to see, look, at some point Jay mentioned, okay, we are able to detect unknown vulnerabilities. The way to verify if I'm right or not in a few months from now is to go and check, okay, how much vulnerabilities were filed by Talos and Hypershield because of things that data that Hypershield detected. Cool. Any questions on this? Nope. Then we'll dive into the last topic of today. Let me see how I'm doing on time. So I think I have 10 minutes
10 minutes left. Yeah, and okay. No questions so far. Good.
Okay. So I'll reuse the last 10 minutes to wrap up here then. Cool. So auto segmentation. Again, very loaded term. Segmentation is, I'm not going to say it's impossible today, but it's very difficult to do, right? Because segmentation, it's not a one-time effort, right? Exactly the same like security, right? It's not it's not a destination, it's a journey, right? The same applies to segmentation. Now, with Hypershield and especially the eBPF bit, we can actually do a few things that a lot of other products are struggling with, right? By having access to eBPF, we know exactly which process is running where, what are the ports, what is some of the SBOM information, a whole bunch of additional information that is used to actually figure out what is this process, right? What is it doing? What should it be able to talk to? What should it not be able to talk to? So just by having that bit already, we have access to certain things that will allow us to do things that others cannot. Combine that then with the fact that we also have AI. And how should you think of AI? Well, that's basically something that in near real time helps us make sense of this huge amount of information to figure out, okay, what is the right way to actually go and segment things. And we can do this at different ways, right? So we can do this by starting to put like, okay, let's log instead of apply. Let's look at identity. Let's look at process IDs. What are those processes doing? What libraries are they using? What are the behaviors that we observe? All types of things. that will actually help you to continuously update what the segmentation should be, right? We can do a fingerprinting thing. We can even look at, okay, what file changes are being made. So because of eBPF, again, when I say it's a superpower, you might think this is the marketing guy and me talking, but it's not that much of an exaggeration, if anything, right? Because now we can see everything inside the operating system, even before things happen on the network layer. So it's not just taking everything on the network layer, it's everything in addition to that inside of the operating system. We can see for processes, what files do they need access to, right? So what if, for example, if you look at the distributed microservices application, you have a process that needs access to a certain file. And then all of a sudden, because the application is scaling out, that file is no longer living on the same system as the process that needs access to it. So as soon as that change is happening, the application itself didn't change. It's just how it's running and where it's running changes. Then all of a sudden, we now need a network socket for this process to still be able to read that file, right? But because we now know that this process needs access to that file, whenever that file is then stored on a different system because it's scaling out, for example, in a Kubernetes environment, then look, we will need to make sure that our segmentation policy allows this process to actually have a connection to that system to go and read that file. And segmentation is now no longer just about what packet is able to go where, which is typically what would be the case in a traditional segmentation approach, but it's now even which process can read which file, which process can change which file, regardless of where that file happens to be at that point in time, right? So it's not just what you can do, but it's based on what information that you can do it and what things that you can segment, right? So it's not just network environments that you can segment, but it's a whole bunch of additional things. And again, there's different layers of what do you want to focus on first, and the AI will again try to do a good job of helping you figure out, okay, what is critical, what's not business critical. If things go down, for example, parts of a link between two big chunks of your network goes down or gets saturated, that the system can actually go detect this and make suggestions on how to deal with those in a different way. So again, lots of flexibility, lots of different approaches for the segmentation bit. Again, most likely it's going to be a journey together. It's not just you install Hypershield and you let it go do its thing. It's going to be a learning exercise as to, okay, what is the best way to use it? How do you deploy it? How would you start doing the segmentation journey? Do you start by having like a log only, then log and apply, or apply and log and things like that? Sky's the limit, right? And this slide should properly follow it. So again, the way that you can do is you can use shields into place for that are different depending on what is the risk of this application or how important is this application. You can put different guardrails. Okay, who can talk to what? You can put policy into place or segmentation policy into place based on legislation, right, or rule sets that you need to comply to. For example, in the financial world, we see a lot of customers showing lots of interest in Hypershield because they can then start translating these legal or these mandatory rule sets or mandatory segmentation policies into place. One thing that we're actively looking into is, for example, having a natural language model added to the AI. So, for example, you could say, look, this is a description of the law, or this is a law on for financial companies on how we should segment our traffic, or this is a law on how to separate personal information or healthcare information and separate that, or deal with that, segment that in a different way, so that actually the system can learn not just from looking at what is happening in reality, but also by looking at, okay, this is rules that we need to comply to, right? So those are all things that are in the pipeline that we're working on. Again, will most likely have a very interesting impact on the way we actually approach segmentation stories. And again, it's all about the building trust stuff, right? Because yes, we can build whatever we think makes sense, but again, every environment is different and unique for all the right reasons, right? So there is always going to be a huge amount of time and effort spent on making sure that whatever Hypershield is proposing to do, that will have like a feedback or a loop cycle that allows you to have influence on what it does, and also the cycle will give you the why or some reasoning as to either why are we doing it, or a combination of why are we doing it, and this would be the end result if you actually go and do it, right? Cool. So I think with that, we put a lot of information on the table. I think we have 5 more minutes left. So any questions, or if any of Lars-Erik or Christian wants to do a final wrap up, all that left for me to say is thanks for the opportunity to speak to you guys. Looking forward to any future interactions, and you still have some time to ask me whatever question you want.
Thanks, Jerome, and thanks everyone for listening. Lars-Erik, you want to close it off?
Yeah, sure. I'm sorry, my brain is full of information now. It was very, very good. So, of course, if anyone comes up with a question after the webinar is done, just contact us at Conscia. We'll be happy to see if we are able to answer them, or we'll just pass them on to the experts at Cisco. Thank you both, Jerome and Christian, for spending time with us today, and thanks for excellent content. I'm sure this isn't the last Hypershield update we're gonna come with. This is a product that seems to be evolving quite fast, and I'm super excited to see, you know, how it moves forward, and also, of course, as the technical nerd I am, being able to get hands-on on it as soon as I can.
Yes, and that's probably the next step, right? So if I can suggest something, if you like it, get in touch with Conscia, and we'll work together with them to make sure you can see what does it look like in real life, perhaps do some demos or whatever. So yeah, do reach out to Conscia. They know how to reach us. Let's get something going.
Cool. Thank you so much, and thanks everyone for attending.
Bye-bye.
Bye for now.